Nitrogen sickness, what's also known as decompression sickness or the bends, as well as soda cans are excellent examples of Henry's Law. Another example of applying Henry's Law that is quite pertinent to our lives today with COVID-19 are oxygen ventilator machines. Ventilator machines are used to increase the partial pressure of oxygen within the alveolar space above what it normally is within the alveolar space. So rather than being 100 millimeters of mercury, that pressure is now increased by increasing the pressurized air that is moved into the lung space, right? Mainly by using high flow oxygen. And when that pressure is higher than it normally is, that means we're going to have a greater pushing pressure and be able to push more oxygen into the blood plasma, right? And this is useful for an individual that is in respiratory distress, that has tissues that are hypoxic, to be able to dissolve more oxygen into the plasma fluid to allow for then more hemoglobin to pick up that oxygen, bind that oxygen so that it can be delivered to the body cells. So that in itself is an application of Henry's Law. In essence, with ventilator machines, we're increasing P so that we can increase C for oxygen. Increase the pushing pressure so we can increase the concentration of oxygen within the plasma. Now, Henry's Law as applied to soda cans, if we have a carbonated beverage, a gas that is under pressure, right, and we open that soda can, what we're doing is we're decreasing the pressure from above. Remember, this is our pushing pressure from above by opening that pressurized can. And when we do that, we decrease the concentration of CO2 dissolved in that soda, in that solution, right? Because now we have a lower pressure outside, higher pressure inside the drink. The CO2 is going to move down a pressure gradient and come out of solution, dissolve out of solution. And that's what I was going to show you with my application of my DrinkMate machine. I just wanted to show you one particular aspect of it. So I'm going to bring it over and hopefully it's not going to interfere with the audio, but if it does, it will be temporary. Okay, so this gets kind of loud. And if the audio is working, you might want to turn it down. How many of you have one of these in your house? And if you do, you can't possibly tell me it's not the greatest invention ever to have a homemade carbonator. I like to spice things up, put bubbles in my water. Ooh, an old-fashioned one with a CO2 bottle and a regulator. Tell me how that goes, David. I want to know if it works. This is not one of the fancy ones, DrinkMate. It's relatively cheap, but it does the job. And I'm not a fan of flavored seltzer, so I just take my tap water, which has all the wonderful minerals in it anyway, right? And I carbonate it. If I can hook it up to the machine, when I press this button, it's going to force CO2 at high pressure into the water, right? So into the fluid. So we have this pushing pressure, physically pushing the CO2 into a solution. And I push the button until it tells me to stop, right? And it will tell me to stop by opening this valve to release the excess CO2 gas. So we'll see how that works. right? That little whoosh that happened tells me that at this point, I have pushed enough CO2 into my water here such that I have matched the pressure in this this air-filled space, right? So now my pressure for my CO2 in the water matches the pressure in the airspace. And if I take this off, in order to actually open it, I have to relieve a little bit of that pressure. But now we see that there's actually some sort of bubbles going on in there. And as I leave this open, that pressure has been relieved above my CO2 gas in solution. And now my CO2 gas is leaving solution, right? Moving down a pressure gradient and out into the airspace. I don't want that to happen. I need to create a closed container. Let me get this out of the way.
So what does that do to the taste? Is it like taste like soda or?
Oh, it tastes like, this just tastes like seltzer water. This is, all I did was put carbonation in regular water. But yeah, you could make soda if you have whatever flavors to add to it, right? It would create soda, because that's all soda is flavors, sugar, and water, and added CO2. CO2 that's been forced in at high pressure. Okay. So that's my demonstration of Henry's Law. And every time I use that machine, I think of Henry's Law, right? Whenever you open up a can of soda and you hear, psh, that's Henry's Law. That's relieving the pressure, as we see here, decreasing that pressure by opening the can and allowing that, that CO2 to move down a pressure gradient towards a lower pressure, and decreasing the concentration of that CO2. You leave that long enough and that CO2 will escape and your soda will be flat. Okay? You know how that happens. So for the rest of our time here, let me talk a little bit about nitrogen sickness or decompression sickness, what's otherwise known as the bends. Partial pressure of nitrogen in the atmosphere, it's around 600 millimeters of mercury. Right? We calculated that with Dalton's law. The partial pressure of nitrogen gas in your blood plasma, as I showed you on the previous slide, is around 573 millimeters of mercury. This means there's very little dissolved in your blood plasma at 1 atmosphere. And that's because of the very low solubility of nitrogen gas. We would need a very great pushing pressure in order to double that pushing pressure of 573 to push even more nitrogen gas within the body fluid and effectively double the concentration of nitrogen gas, right? So in essence, at sea level, the concentration of nitrogen gas is very low in your body fluids, and it is biologically inert. Your body cells do not utilize nitrogen gas, and at those levels, it doesn't interfere with any normal physiological processes. However, once we begin to increase the levels of nitrogen gas within the body fluids, then that can lead to issues, especially with neuronal activity and the ability of your excitable cells to function appropriately, potentially leading to CNS depression, as we'll talk about. Underwater, right? Atmospheric pressure rises every 10 meters or 33 feet. We increase by 760 torr. We increase by 1 atmosphere, right? 760 millimeters of mercury. When you're diving, you're breathing compressed air. You're breathing under pressure in order to ensure that under that greater pressure, you are appropriately pushing oxygen into your blood plasma to produce the same concentrations that you would generally normally see at sea level, and allowing for CO2 to be removed at the same concentrations. So these diving tank mixtures of gases are calculated, devised in certain ways to ensure that when you're breathing under pressure, you're getting the appropriate amount of oxygen into your blood plasma and removing the appropriate amount of CO2 at those greater pressures. Nitrogen gas being very low in solubility, with compressed air, breathing compressed air, means that more nitrogen gas will be dissolved in your blood plasma with that increased pressure. So as you're diving to depths, you're increasing the concentration of nitrogen gas within your body fluids. The problem comes when you surface. If you surface too quickly, without the appropriate measures for decompression, which generally means that you meet certain requirements in terms of surfacing to a certain depth and waiting a time period, and then surfacing to a higher depth or what have you, and continue that decompression. If you don't do that, if you surface too quickly, then the nitrogen, with its very low solubility, it will just come out of the plasma. You're relieving that pressure too quickly, and it already does not want to be in solution, has very low solubility. It quickly comes out of solution. And it will come out of the plasma anywhere in your body, but especially in places of least resistance, like your transcellular body fluid compartment, your joints in particular, causing great pain, right? Causing you to double over, leading to the bends. In essence, your body becomes a human soda can that has been opened, right, with decompression sickness. In order to treat this pain that is occurring and potential damage to smallest of capillaries, say in your brain and in your kidney, a hyperbaric chamber can be used, a pressurized chamber with high oxygen flow. The pressure in that chamber will help push the nitrogen gas back into your body fluids. Or if you are still diving, you submerge to depth in order to allow for the appropriate decompression. You need to bring yourself back down and decompress appropriately in order to relieve the oxygen, allow it to come out of solution at a slower rate so it doesn't cause this pain and damage. Right? Now, in terms of the types of diving gases that can be used, a mixture of gases that can be used, with what's called saturation diving. This is generally deep commercial diving that's being done for long periods of time. A mixture of oxygen and helium is used in combination, which generally referred to as heliox mix. And this is used to prevent nitrogen narcosis, using helium rather than nitrogen, in order to decrease those potential effects that we might see with nitrogen at very high levels within the body fluids, and how it might affect the ability of your body cells to function appropriately. And I'll describe that in just a minute. But the effects are called nitrogen narcosis when it does happen. So using a mixture of oxygen that your body cells need, but helium replacing the nitrogen, can be used in those types of situations as a breathing gas mixture, pressurized breathing gas mixture. What can also be used is trimix, which is oxygen, helium, and nitrogen, where helium is being used to substitute for some of the nitrogen in that mixture of gases to help prevent nitrogen narcosis. And in that type of mixture, the oxygen can actually be optimized for whatever specific depth limit that you are diving to, in order to help decrease the risk of oxygen toxicity, having too much oxygen pushed into your body fluids, which can also be a problem. So these mixtures are calculated very carefully for whatever dive that the individual is going on, whether it is a commercial dive, deep commercial dive, or it is a recreational dive that is calculated in advance. Because at depth, all of these gases do interfere with neuronal activity. Under pressure, CO2 doesn't stimulate your medulla oblongata, respiratory center, like it usually should. And what happens is you forget to breathe, right? Your body forgets to breathe. So you begin to hypoventilate at depth, and that can lead to CO2 blackout, where now your body is retaining too much CO2, you're trapping too much CO2, and that can lead to blackout, lead to loss of consciousness. The type of effect we see with nitrogen, called nitrogen narcosis, is also referred to as the Martini effect. It feels like you're drunk, even though you haven't been drinking. And this is because that those high levels, or that high concentration of nitrogen in your body fluids, is leading to central nervous system depression. It's interfering with the ability of the neurons to fire appropriately. And then oxygen and helium at high levels, high concentrations within the body fluids, can induce both seizures and comas. I just want to point out that there is a link here to an article from a 2005 magazine issue of Outdoor magazine. And this is the Dave Shaw story, No Relation to Me. Dave Shaw is a deep sea diver, or was a deep sea diver from South Africa. And this story, Raising the Dead, is about a deep sea dive, or I should say several deep sea dives that went terribly wrong, where at depths, gases that were part of these pressurized mixture began to interfere with neuronal activity and led to problems with CO2 blackout, with the Martini effect, and in the end, death of several individuals. The moral of this story in this magazine is, I guess, always to dive your plan. I guess that's a mantra for individuals who deep sea dive. Dive your plan. Don't deviate from that dive plan, because things can and will go wrong, given that you've calculated what you need and what depths you're diving to, and your decompression points in advance. Right now, I wouldn't know this personally because I've never deep sea dived, and I never plan to, especially after reading this particular story. So it's a fun read, right? All my work with diving has all been surface work with my PhD field work, with a snorkel on in maybe 5 inches of water, right, to do my field studies on fish. And I would begin to hyperventilate if I went into deeper water. So I'm not a fan of diving deep, and after reading this, I had nightmares. So it's been a while since I've actually read this story to recall what exactly happened. So if you're interested, I'd say take a read, but I'll just give you the Cliff Notes version of this story, so you have an idea of what it's about. So it begins with a diver, Dion Dreyer, and Dion Dreyer decided to dive into Bushman's Hole in South Africa, which is the 3rd deepest freshwater cave system, to depths of about 927 feet. Remember, every 33 feet in depth below sea level is 1 atmosphere. So on average, that's about 30 times atmospheric pressure. You dive down to depths of 927 feet, 30 times atmospheric pressure, which means that upon surfacing, it takes roughly 9 hours to decompress to avoid decompression sickness, the bends. We begin with Dion Dreyer, who is on this deep sea dive. I shouldn't say deep sea dive, it's a freshwater cave. So he's down at depth and he's exploring these caves, and he doesn't follow his plan appropriately. He ends up hypoventilating because of high CO2 levels, and he undergoes a CO2 blackout, loses consciousness, and he dies, right? Since he was by himself, his body was not recovered. So flash forward 10 years. 10 years later, a diver by the name of David Shaw, once again, no relation to me, and his dive partner, Don Shirley, decide that they're going to attempt to recover Dion's body, that they are going to dive with a body bag and cables to attach to the body bag so that the body can be removed. Dave is the one who's going to dive to depth within the Bushman's Hole down to these freshwater caves, and Don Shirley is going to be his first decompression point. He waits for him there at the first decompression point while Dave dives to depth. Dave dives, he finds Dion's body. At this point, 10 years later, Dion's body is now decomposing, and decomposing in water means that generally the hydrophobic material of the body is still present, the fat. So the body begins to float, all right, as he's trying to put it in the body bag. So here he is attempting to put Dion's body into a body bag, and the body is floating around, and he begins to get tangled in the cables that are attached to the body bag, and he begins to breathe heavily, right, with his ventilator and his pressurized air. And he begins to undergo a CO2 blackout. First, it begins with nitrogen narcosis because he's breathing in too much of the nitrogen, becomes disorientated, and then he forgets to breathe, and that leads to blackout. Now that he's blacked out, he's not re-emerging, resurfacing at the rate that he should. Don is checking his dive watch, dive calculator, to see that he should be arriving at a certain point in time, and he's not, which means he's running out of gas. Right? He's running out of his mixture. Don now attempts to dive to depth, but he's not conditioned to dive to the depths that Dave is. He ruptures his eardrum trying to dive to depth. He breaks his dive calculator while trying to dive to depth. And then, because his dive calculator is broken, he surfaces too quickly, and he ends up with the bends, with decompression sickness. He survives that decompression sickness, but he does have permanent balance impairment because of his ruptured eardrum. Later on, both Dave Shaw and Dion Dreyer's body were recovered. And upon that recovery mission, apparently, they did not have to dive to depth because both Dion's body, which was floating, right, which was buoyant, and Dave Shaw's body had gotten tangled in the body bag cords, and they had risen to the top, right, near the surface, and were just under an overhang. And so both of those bodies were collected near the surface at Bushman's Hole. The end. Doesn't that just make you want to go out and deep sea dive?
Okay, so the person died to rescue another dead person.
Yes, Dave Shaw died trying to recover the body of another diver who had died 10 years earlier. Yes. All of this being problems with the dive plane gone wrong, right? Knowing that you have exact amounts of gases, breathing gases, you have exact times that you have to be at these certain decompression points when surfacing and all of that. And should one itty bitty iota of fact here go awry, then these types of issues arise, both in the case of originally Dion Dreyer and then Dave Shaw. Yes, David says almost the whole squad. Yeah, Don Shirley was the only one who had survived and did not get away unscathed in terms of the damage to his body after that. Yeah, it is a sad story. It's scary. Like I said, it's been a long time since I've actually read it, but it's one of those things that just like sticks in your mind because it's just so terrible. But if you're looking for something to do during your home stay, it's not a short article, but it is really interesting to think about how these gases influence you at high pressure and high concentrations within your body fluids. Yep, that's the article right there. Yeah, and this link on my screen that you have in your PowerPoint will also get you to the article as well. Thanks for sharing that, Shannon. My advice is just don't deep sea dive. To me, it seems too complicated. I say leave the deep sea to the fish and the other weird creatures, the invertebrates that live down there. We've got machines, we've got cameras, we send those down. Take a look at them if we really want to see that. Send those into the caves. That's what I say. Now, having gone through all of that, let me just tell you that the portion of the final exam that is respiratory, I might ask you maybe a question or two about how this type of topic relates to Henry's Law, but I'm not going to ask you details about this story, for instance, or the different types of mixtures of gases you would see for deep sea diving. That's just useful information if it's an activity that you're interested in, that's something that you do, or something you want to try and you're kind of leery as to what that all means, right? If anything, hopefully it deters you. I'm going to go drink my seltzer water now.